So page 83, it says, we wish to estimate the percentage of U.S. adult population that has hyperthyroidism. A random sample of 400 U.S. adults shows that 46 have the disorder and require medication. Okay. So we have a sample of 400 people, and we show that 46 out of the 400 have the hyperthyroid. Just so you all know this, if you are male gender, your thyroid will stop working at a huge amount of probability by age 40. I didn't know mine wasn't working until I had went and got a physical and they did the blood test going, have you been really tired? And it was in the middle of summer. I'm like, no, your thyroid's not working. So now I got to take this little ground up pig thyroid pill for the rest of my life. Not a big deal. I didn't know it wasn't working. I guess now it's still not working, but now I have medication to supplement. Okay, so what is our population of interest? Our population of interest are U.S. adults. Okay, you might be able to say U.S. adults with this hyperthyroidism. And what is the sample? The sample is 400 U.S. adults. And number 3, what is the point of estimate as a percentage? So I'm going to go 46 divided by 400. So we are thinking that 11.5%, so that's just 46 divided by 400 adults with hyperthyroid. Okay. And then construct a 95% confidence interval. Okay. The first thing I'm going to do is we have to do a normal distribution. Okay. Being that we don't have the mean and the standard deviation, we're going to say that our mean is equal to 0 and our standard deviation is equal to 1. Okay. Yes, we do have an average, but that's not what we're worried about. And then I need to figure out what the halfway to 100 would be. So from 95 to 100, what's halfway to 100 from 95 to 100? Yeah, 97.5. Okay, so 97.5% is the halfway to 100. Okay, does everyone feel comfortable with that? Okay, so I know that that is going to be the same thing as 0.975. Okay. All right, so construct the interval. So we're going to do the interval. So we're going to jump on to Desmos and plug this in because it'll handle it nicely for us. Graphing calculator. And so I'm going to go normal distribution 0, 1, which that gives us our normal distribution. And then I need to go period, and I forget what it is. I have to look it up. So under functions, it's inverse something. Inverse CDF. So then I'm going to do inverse CDF. And guys, we realized I signed the wrong page, so we're on page 83. So just fill it out and I'll give you the points for it. Cool? Yeah. Sorry, I made mistakes. Okay. And my inverse CDF, I'm doing 0.975. So that's going to give me 1.96. Okay, which means 1.96 standard deviations from the mean of 0 in this case, would encompass 97.5% of the population. So that means that at our tiers, we have basically, 2.5 divided by 2 and 2.5 divided by 2 at the ends of our normal curve. Okay, so 1.96. Okay, so this is gonna show that our Z star is 1.96. Okay. So then from there, what we're gonna do is we're gonna go back in on 5.7. Need to look at Z star. So P minus 1. Okay, so then we're gonna go. Let's call it what? Let's call it our MOE, our margin of error. So it's going to be Z star P1 minus P over N. Laura, we're on page 83. And I assigned the wrong page yesterday because I hit my head or something. All right, so there's information that we already know. So we know our Z is going to be 1.96. I know that my percent is this 11.5, so I'm going to go 0.115, and then I'm going to go 1 minus 0.115 over our sample, which is N, which is 400 people. Okay, and so decimal should handle that nicely. Write this down so I don't have to flip back and forth to it. So 1.96 root 0.115, 1 minus 0.115, all divided by 400. Bless you. And we should be able to plug that into Desmos as well, and it'll handle it nicely. So I'm going to go 1.96, and then square root, make a fraction in there. And we're going to go 0.115 parentheses 1 minus 0.115. And then that's going to be divided by 400. So that answer comes out to about 0.03. Okay? So this is 0.03. Okay? All right, so our confidence interval will be 11.5% plus or minus 3%, which takes us from 8.5% to 14.5%. Okay? So that is the answer for number 4. This is all kind of goes with 4. Does this confidence interval provide evidence to support the following statement? More than 10% of U.S. adults have hypertension. Okay. So does this show that more than 10% have this hyperthyroid thing? Okay, so what you're going to look at is we're going to look at this. Okay, is that confidence interval of 8.5 to 14.5 above 10%, below 10%, or does 10% fall within it? It falls within. So we don't have evidence to say that more than 10% of the population has this, okay? Because in a confidence interval, our mean, basically what we're looking for, or our parameter, is within that. So I could show with my confidence interval being 95%, I could show that we could have our mean or our parameter at 8.6%. Okay, 8.6 is a smaller number than 10%. So no, 10% is within our margin of error. Okay, this is the margin of error. Does that make sense? Okay, now people could argue, yeah, but 10% is within it and it's kind of at the lower end of it, so it might mean something. That's the bad statistician. The person who's doing the statistics is trying to protect themselves and saying, hey, we got a margin of error, and somewhere within that margin of error, we're 95% that our parameter or our mean, I'm kind of using those, as the same term, is within that, so we can't justifiably say that. Now, if that showed like, let's say our 3% was smaller, so our margin of error would be, say, from 11% to 12%, then that's going to mean something a little bit different. Okay? That would then show us evidence that didn't indeed take place. Okay? Did I say that clearly? Okay. Yeah, Mila, we're on page 83. I'm just going through it. I assigned the wrong page yesterday. Sorry. All right. Is the sample size large enough to meet normal assumptions for this population? Okay, so this kind of goes back to the quiz. So we had a sample of 400. Okay, so this is greater than 30. Okay, so it works there. But then I'm going to go, is n times p greater than or equal to 10? Or is n times 1 minus p greater than or equal to 10? I want to pass these two things. And the reason I'm going with those is I have the percents that I found up above. Our percent, 46 out of 400, is 11.5. Okay, so if I go 0.115 times 400, is that greater than 10? Well, I'm pretty sure it is, because if I just multiply by 0.1, I get to 40, and I'm above that, so this works. And then is 400, and then 1 minus the 0.115. So 1 minus 0.115, that gives us 0.885. Is that greater than 10? Yeah, 88% of 400 is much larger than 10. So we have justification that this is going to work. Okay? State the critical value for the 95% confidence. What does this measure? Well, our critical value was 11.5. Okay, that was the value we found, 11.5%. So state the critical value for 95% confidence, 11.5. What does this measure? This measures the percent of our sample having hyperthyroid. Okay? State the margin of error. Explain what this means in the context. Well, our margin of error we found up above, 8.5 to 14.5%. Okay? So we are 95% confident that our parameter, and again, the parameter and the mean are kind of the same type of term, fall within. Okay? And then number 9, briefly explain what would happen if the margin of error if the confidence interval was increased to 99%. Okay? So if I went from 95 to 99%, my margin of error, or my confidence interval, would be larger. Okay? Okay, the higher percent, the broader out, the further out on the normal curve that I would go. I'm already at 95% confident. If I go to 99% confident, my margin of error might get all the way out to 6% to 16% or something like that. So we're stretching that much further out to say, could I be 100% confident that everything fell within 200 standard deviations of the mean? Probably. Okay. So that should help you with that. And then number 10. From a random sample of 50 tax returns filed with the IRS, 17 of them contain errors. Wow, that's 34% of them, right? Construct and interpret a 90% confidence interval to estimate the percentage of all tax returns with errors. Show the setup. So then we go to number 10. They tell us that we have our sample is 50, and we know that 17 out of 50 is wrong. So that as a percent becomes 0.34 if you want 17 divided by 50, which is 34%. So now what we're saying is, hey, 34% of tax returns filed are wrong. Okay? I think the IRS is going to be a little bit busy if that truly is a fact. Okay, so first thing I want to do is I want to find my z-score. So again, we can do that pretty easily. We're 90% confident. So what's halfway to 100? 95? Do you agree? Okay, which means I'm going to plug 0.95 in. And I'm going to try and get my z value out of this. So my z value is going to be found from Desmos. So I can use this. I'm going to change this just to 0.95. And so that means that 1.6 is my z star. That's my z goes along with the z-score. So that's how many standard deviations would encompass. So we have 1.6 roughly. So this is going to give me 1.6. Okay. And then my z star times the probability minus 1 minus the probability over the sample. This is going to give us our margin of error. Okay, so I'm going to go 1.6 times 0.34. And 1 minus 0.34 is 0.66. Did I do my math right? I hope. And over 50. And we can do that on the calculator pretty easily. So 0.34 times 0.66 divided by 50. Take the square root of that times 1.6. So my margin of error is going to be plus or minus about 0.11, which is about 11%. I rounded it, okay? Which then means we knew that 34% was our error. And if I go plus or minus 11%, this is going to find our margin of error. So 11 minus 34 is 23%. And then 11% added to 34% is 45%. So friends, we are 90% confident that our parameter of incorrect tax returns that are filed will fall somewhere between 23% to 45% of the general population. Friends, that's not good. That's not good at all. No wonder why the IRS is like the 5th largest employer in the federal government. Yowzers. Huh. I don't know. Guys, I'm getting a little goofy. I like this stuff. I'm sorry. Okay. And then number 11 says, according to a random sample of 600 households, 360 of them had a television tuned into the Super Bowl last year. Construct and interpret a 92% confidence interval show our setup. Okay. So number 11, our sample is 600. And we're going to say that 360 out of 600. So this is 0.60. So this is saying 60% of households watched the Super Bowl last year. I guess it could go with this past Sunday. I don't know. So that kind of works. And we have a 92% or 92% we are certain. So what is halfway to 100? Well, 100 by 92 is 8. 8 divided by 2 is 4. 4 out of 92 is 96. So that's 0.96. Okay? So we can plug that into our buddy Desmos. 0.96. That's going to give us a z-score of 1.75. Okay, did I say that right? 1.75. Cool. All right. Oop, hang on. Let me check something real quick. Yep. All right. So then I'm going to go my z star times the probability minus or times 1 minus probability over n. So that's going to give me 1.75 square root. We have 0.6. 1 minus 0.6, which is 0.4 over 600. And calculator should handle that pretty nicely. 0.6 times 0.4 divided by 600. Take the square root of that times 1.75. So this is going to give me 0.035, which is 3.5%. So then our confidence interval is going to be 60% plus or minus 3.5%. So that's going to be 56.5% to 63.5%. So friends, we are 92% confident that our parameter of TVs that are watching the Super Bowl a year ago would fall somewhere between 56.5 and 63.5%. And friends, that is 5.7. Let's see, is attendance right? I think I have it right. Cool. All right. So, uh-oh. Here come the singers. All right, I'm on page 17. Not us? You didn't bring him? You let him down here. All right. Page 17. Here we go. We got time. So I might not get all the way done with this, but let me start it. That should be good. All right. A one mean Z interval is very similar in structure to the one proportion Z interval, which you just did. However, the sample means have different standard error procedures as outlined by the formula. So they're now saying that you have a standard error, which is the standard deviation over the sample size, square root of the sample size. Once again, the Greek symbol sigma stands for population standard deviation. So that's the population standard deviation. We must know the population standard deviation to create this confidence interval. The point of estimate of our margin of error is going to be Z star times sigma over the square root of n. So a company develops a test of leadership skills. The test is given to 50 applicants for a job. The average of these scores is 84. Assume that the standard developers know that the standard deviation for all these tests is 12. Create a 90% confidence interval on the average test score. Okay? So they're saying the point estimate is equal to 84, and that was given to us from the reading. Okay, that was the average test score. The margin of error is going to be our Z star times this, which we already have written. So we have to figure out Z star. So Z star, we're going to use our buddy Desmos. And we are 90% confident. So 90% confident, halfway to 100 is what? 95? So that's 0.95. So we should be able to handle that on Desmos. So I'm going to change my 0.96 to 0.95. So we're at 1.6. Okay, which they don't have listed, but that's fine. So this is going to tell us that we're going to have 1.6 times our standard deviation they told us was 12 over the square root of our sample, which was 50 applicants. And so we should be able to handle that. 12 divided by the square root, clear. Square root 50, 50 square root, 7.07, 12 divided by 7.07 times 1.6. So that's going to give me, they're off a little bit on theirs because I rounded. So I'm coming to 2.72. Okay. So we are 90% confident that our estimate of 84 is accurate within 2.72 test points based on what I just did. So we're going to go 84 plus or minus the 2.72. So that's going to give us a confidence interval. And I know mine's off a little bit because I rounded too soon, but that's okay. So our top our top of our mark is 86.72. And our bottom is 84 minus 2.72. Clear. So 81.28 to 86.72. So we are 90% confident that our parameter our true average of leadership is between 81.28 and 86.72 as far as mine goes. Okay? So pretty straightforward. And look at that, my friends. Stirrup is done. So perhaps I could give you the right page that'll be due. We'll work it tomorrow in class as well. Hopefully you guys are getting your sheets of paper set up. Getting your sheets of paper set up because we have a test on Friday. Okay, so this time I think I'm right saying page 8586. And I know some of you had already started it because I gave you the wrong page yesterday. So it should be kind of less. And that is all I have.